Okay, so where we left off last class was working on this problem, and we're trying to find the extrema of this original. So this is the original, and we're trying to find extrema. So when I say extrema, I mean the highs and the lows. Why do we care about extrema? Maximizing profit, maximizing revenue, minimizing cost. Right? So if I can find those points, then I'll know how much to produce, how many hours, whatever the situation is. So we're not putting it in a word problem yet, but that's kind of the future. That's why we do extrema. Okay. So remember, it's all about the original. It's all about the original. It's all about the original. We'll be doing derivatives to find these extrema. But again, the main message, it's all about the original. So as soon as I say find the extrema, notice this one has a domain of 0 to 6. The very first thing you should think of is stationary, singular, and endpoints. That's the very first thing you think of. Now, what is this process, stationary, singular, endpoints? What we're saying is to find your potential, your possible extrema, highs and lows, we go through this process called stationary singular endpoints. Stationary are the typical top of the mountains, bottom of the valley. Singular are those weird sharp corners, and endpoints are where it begins and where it ends. Those are the places we need to look. So how do you find stationary? Well, to find stationary, you take the derivative of the original, that's 3x squared minus 18x plus 24, and set it equal to 0. Now, as we do that, you have to know how to take a derivative. Okay, so that's step one. You got to know how to take a derivative. Step two, we set it equal to 0, which means you need to know how to solve. Yes, this is quadratic. You're totally welcome to use quadratic formula. A is 3, B is negative 18, C is 24, but I'm going to go ahead and factor it. If you factor out a 3, you'll get x squared minus 6x plus 8 equals 0. That factors to x, and you get minus 2 minus 4. Set each piece equal to 0, each piece equal to 0, and solve. So from this process, we get two answers. We get x equals 2, and we get x equals 4. Now, it looks very straightforward. Again, you can do quadratic formula in your calculator or whatever to double check that. But if you don't know how to take the derivative and you don't know how to do the algebra, that's where you're going to get stuck. Okay, it's not really extrema that's the problem. It all goes back to algebra. Okay, then singular points. Singular points, we look at the derivative, and we try to find out, are there any places where this is undefined? Any number that you can plug in that would be undefined? And undefined is like dividing by 0. There's no dividing going on here at all. There's no dividing with a variable in the denominator at all, which means there's going to be no singular points, none. And when we look at the graph, there's going to be no sharp corners or anything weird like that. And then the last one is endpoints. Endpoints come from the domain. So your domain, which means it begins to exist at 0 and it ends to exist at 6, means there's two other points we need to look at. 0, where it starts, and 6, where it ends. Okay, so that's the first part, is stationary singular endpoints. Then we're going to use that information to make a table. And the table is focusing on what we found. We have to check out 2. We have to check out 4, we have to check out 0, and we have to check out 6. And where am I going to check it out? I'm going to check it out by plugging it into the original. Why? Because it's all about the original. Now, not to be confused, but there's another way of doing this with a sign chart. The sign chart uses the derivative to see if it's increasing or decreasing. We're not doing it that way, but you could, right? We did a couple examples. We're going to do it by graphing. Okay, so I'm going to pause at this point, see if there's any questions. And if you did to this point, great. The next step is fill in the table, have the graph, verify, is it a max, is it a min, what we have. We know that there's two possible extrema with these stationary points and two possible with these endpoints, but we need to check to see if they are. Do is we're going to go to our calculator. We're going to go to our calculator. We're going to go to y equals, and in y1, we're going to put the original. So that's x raised to the 3 minus 9x squared plus 24x subtraction 10. Okay? Then I'm going to go to the table feature. I'm going to go to the table feature and plug in those numbers. So I go to the table feature, second graph, get rid of any numbers we have in there by deleting, and 2, 4, 0, and 6. This is now giving me specific locations. So I go to my table, and at 2, we have 10. So I'm going to go check out 2, 10. At 4, we have 6. So I'm going to check out 4, 6. At 0, I have -10. Right? Yep, -10. So 0, -10. And at 6, we have 26. Now, these are the exact places I need to look. Those are the exact places I need to look. But in order to look to see if they're extrema, max, or a min, or what they are, what you need to do is graph. So now we need to focus on graphing. Now, remember, you are given a domain. A domain is really important. It says that this is going to begin to exist at 0. And this will end existing at 6. So it already tells me what my x-axis needs to be, 0 to 6. Nothing before 0, nothing after 6. So that already takes care of my x-axis. And then the y, I don't know. Well, we look at the y values. The lowest is -10. The highest is 26. So I'm going to go to like -15, below the -10. And I'm going to go to like 30. And I'll count by 5s. Nobody is going to tell you the window. You determine the window based on the problem and what you need. And the big question is, how do I know if I have the right window? How do I know if I have the right window? Well, let's look at the points. 210, right? Zero, -10, right there. And 626, right there. Can I see all of my dots, all of my points? Yes, that means you got a good window. Okay, so we go to the calculator. Again, no, we're going to go x minimum 0, x maximum 6. I'm going to count by 1s. The y, we're going to go from negative, bless you. What do we do? -15. Up to 30 and counting by 5s. Now, again, all this needs to be done by you before I go over it. That thinking, I'm taking it all away if you're just copying, right? And this is not the first example. This is like our second or third example, right? Hit graph. That's what it looks like. And it follows what we drew, right? There's our dot. So it goes up, down, and up again. Okay? So as we look at each point, we're going to figure out, is it a max, is it a min? So we're using the table to figure that out. So 0, 10, we're going to go ahead and call it out loud. What do we have there? Local max or local min? Local max. Why? It's a high point. It's the top of a mountain. To the left, it's lower. To the right is lower. It's a max. 4, 6. What do we have there? Local min. How do I know it's a min? It's the bottom of a valley. To the left and right are higher. You have to walk down to it. 0, -10. Be careful. What do you have there? Local. Keeps coming up. Sorry. A local min, right? We have a local min. And again, if you're like, how is it a min? To the right is higher. You have to walk down to it. A couple different ways of looking at it. And then what do we have at 626? Local max. Okay, so this would be a classic standard extrema problem, right? Yes, you could do the sign chart, but we'd have to check all the areas in between. I think it would be a lot more work. But this method, you have to know how to graph. You have to know the window. You have to know your algebra. You have to know your derivatives. There's a lot built into this problem. There's a lot built into this problem. Okay, and with that, we're done with the first section. With that, we're done with the first section. Okay, remember the last problem we did do is a little weird, but looking at a derivative and talking about the original, the only couple things I'll talk about is when you're talking about a derivative, if your result is negative, that means decreasing. If your result is positive, that means increasing. And if your result is negative, that means decreasing. So a derivative is rate of change. If you get a negative, it's decreasing. If you get a positive, it's increasing. A little weird to look at it backwards. And then we come to our second section. And our second section, again, it's a ton of extra problems if you ever want to work on them. More than welcome to. The answer to the match ones are there. Okay. The second section is focusing on second derivatives and graphs. Okay. Now, why do we take a second derivative? Okay, wait a minute. A first derivative tells me rate of change, how the original is changing. What the heck is a second derivative? A second derivative is how your rate of change is changing. And you're like, what? That makes no sense. Okay, here's what a first derivative is. My mom lives in Cocoa Beach. So if I go to visit my mom in Cocoa Beach, I'm probably not going to go 10 miles per hour. I'm probably going to go what? 60, 70 miles an hour, right? I'll get on the Beeline or whatever it's called, 520, and I'll run down to Cocoa Beach, right? That speed, 60 miles per hour, is the first derivative. That's how fast I'm going. Are we okay? Now, I live in Kissimmee. I'm driving to Cocoa Beach. When I leave my driveway in Kissimmee, am I going to go 60 miles an hour right off my driveway all the way to Cocoa Beach? No, no, no. My rate of change changes. I start at 0. It goes up to maybe 15 in my neighborhood. I get to, let's say, John Young. Now I'm going 45 miles an hour. I get to 192, and like everyone else, I'm going 80 miles an hour. No, we go to like, let's say 50 miles an hour. Then I finally, whatever I go, blah, blah, blah. But my rate of change changes. And a word that you're familiar with is called acceleration. Accelerating or decelerating. That's second derivative. How your rate of change is changing. Now, they start off with a not glamorous example of second derivatives. So let's go over that first. First of all, concave up. Concave up is when the graph forms like a U. I like to say concave up is like a smile, okay? Concave up is like a happy face, okay? That would be considered concave up. And again, you can see that it's increasing. If it kind of makes a sad face, that's called concave down, like they're down, they're sad, okay? Now, second derivatives can help you figure out when you're in a concave up area and when you're in a concave down area. And your first reaction should be, I can just graph it and see it that way. You're totally correct. That's why this is not a glamorous example of second derivatives, okay? So we know what concave up and we know what concave down is. And we're gonna add that to second derivative. Now, the topic, the idea of second derivatives, I can teach it to you in like 10 seconds. Ready? How do you take a second derivative? You take the derivative once, and then you take the derivative again. There you go. Let's all go home. That's the second derivative, okay? So if you had the original x cubed, let's say you had the original x cubed, and I asked you to find the second derivative. Well, again, little details. The first derivative would have 1 prime, 1 apostrophe there. That's to signal that that's the first derivative. So the first derivative would be 3x squared. Good so far? The second derivative would have 2 primes. That's to signal it's a second derivative. What's the second derivative? What's the derivative of 3x squared? 6x. Done. There's the whole lesson. Okay? Now, trust me, and you don't have to even trust me, I'll show you on the calculator. Let's graph x cubed. Okay, so I'm going to go to the calculator. You're welcome to follow along. Go to y equals, clear everything you have in y1, and let's put in x raised to the 3. Good so far? Then, because we messed with the window, if you press zoom 6, that gets you back to a standard window. Zoom 6. So basically, what does x cubed look like? Well, it's called a hyperbola. Looks like this. We good so far? Now, this is the not glamorous example, so kind of bear with me. If we plug in a number into the second derivative, let's say we plug in -2. If we plug a number into the second derivative, like -2, you get a result of -12. Now, to be honest, I don't care that it's -12, but I do care that your result is negative. If you plug a location into your second derivative and your result is negative, you are in a concave down area. So again, if we look at the graph, here's -2. Notice this portion of the graph is a sad face. Now, if I plugged in another point, let's say 3, into the second derivative, you get positive 18. And again, I don't care that it's positive 18. What I care about is that it's positive. And if you get a positive result in the second derivative, now you're in a concave up area. So if I kind of go 1, 2, 3 up to 18, notice that this portion of the graph is concave up. Now, again, none of this is earth-shattering. None of this is like, wow, my whole life has changed. It's just a nice what the second derivative can do. It can tell you when you're in a concave down area, and it can tell you when you're in a concave up area. You're saying, I could just graph it to see that. Perfect. Before we had graphing calculators, this was a quick way to find out where we were. Good so far? But something unique happens if we, in this case, plugged in 0. If you plugged in 0, you get a result of 0. Now, 0, the number itself, is neither negative nor positive. It's neutral, right? So you're not in a concave up area. You're not in a concave down area. Where are you? You're at this really interesting place that we're going to play with a little bit later called an inflection point. And an inflection point, put it in your own words, is where it changes from concave up to concave down, or vice versa, from concave down to concave up, okay? That's where the change happens. That's where that change happens, where it changes from concave up to concave down. Now, that inflection point is where things are changing. So maybe your revenue's turning around. Maybe the market is turning around. Maybe interest rates are going down. That inflection point is kind of like a marker to say, hey, things are changing now. Instead of being a sad face, we're going to start going into a happy face. It's like a signal of what to come. Are we okay? That's going to be very important in a little bit. But before we do that, let's put a little bit of notes with this. So how do you find an inflection point? To find an inflection point, step 1, you take the second derivative, set it equal to 0, solve for x, and then plug x into original to find y. Now, we're going to do all this later. But just so you have good notes, anytime that I say find the inflection point, what do? You take the second derivative. Again, you have to know derivatives. You set it equal to 0 and solve. That means you need algebra again. Once you find the x, that's great. X is in a location. I need the y, x and y to find the location. So you take the x, plug it into the original, and find the y. Because an inflection point is literally a point x comma y. Okay, and you're like, why aren't we doing that now? Well, I just taught you the idea of a second derivative. And you're like, that is so easy. A second derivative is so easy. All you have to do for a second derivative is take the derivative once and take the derivative again. And you're kind of right, as long as you know how to take a derivative. So let me test you. Here is a function, cube root of x. Take the second derivative. So we know to take the second derivative, you take the derivative once and you take the derivative again, but this one's a little more complicated because it needs to be rewritten first. So the cube root of x, it can be rewritten as x to the 1/3. And that's where people get stuck. If you don't know that, you can't do it. You leave it blank, you get the whole thing wrong. Because you don't know that. That's exponents, right? That we covered in this class as well. So that's a 1, that's the 3, that's where the 1/3 comes from. Then, oh my gosh, I'm asking you to take a derivative of fraction. I have to know fractions? Of course you need to know fractions. We're in calculus. So if you take the derivative, that's 1/3 x to the 1/3 minus 1. You can use your calculator, do whatever you want, but you get -2/3. That's the first derivative. Now, some of you are going to say, wait a minute, he always tells us to make the negatives positives, but we're not done yet. We're not done yet. So I'm going to pause again, and I'm going to ask you to take the second derivative, then clean it up. So if you were stuck at that first step, now I did the first step for you, you finish it off. Okay, let's see how we're doing. And then fractions. 1/3 times -2/3 is -2/9 x. And then -2/3 minus 1. Again, if you're like, how am I supposed to know that? Well, number one, you got a calculator. And number two, you can do it in your head. That's going to be -5/3. But if you're not sure, you can literally do parenthesis, -2/3, keep it in parentheses, minus 1, enter, math, fraction, enter, -5/3, right? So I'm not a big fan of excuses, right? So -5/3. Yes, you could leave that alone. Yes, you could leave that alone, but I like to have positive exponent. And again, we only move the exponent, not negative numbers, negative exponents. So I would probably do it as -2/9 x to the 5/3. That would be a final simplified second derivative. So again, the concept of second derivative is take the derivative twice, but again, you have to know how to take a derivative. You got to know your algebra. It's all going to be there. Okay, now back to the inflection point. So we're going to scroll down a bit. We're going to scroll down a bit. And again, yes, we could have e to the x, yes, we can have ln. All those things are coming back, right? So make sure you still remember your special cases. But we're going to now focus on inflection point. So as we already discussed, I gave you a preview. To find an inflection point, you take the second derivative. You're going to, well, this is with a sign chart. We don't do it this way. That's of doing a sign chart. We're not doing the sign chart. Okay. So here is your function. 4x to the 3rd plus 6x squared minus 72x minus 30. And the instructions are find the inflection point. So to find the inflection point, one more time, you need to take the second derivative, set it equal to 0, solve for x. Once you find x, plug it back into the original, find y, and then here's the bonus part. Make a graph of this, and verify that it is an inflection point. Verify it is a location where it changes from concave up to concave down or vice versa. Okay, so again, take the second derivative, set it equal to 0 and solve. Inflection point, step 1, we take the second derivative. So the first derivative is 12x squared plus 12x minus 72. The second derivative, you take the derivative again, 24x plus 12. Okay, questions on the second derivative? Be careful showing all your work. Then we take that second derivative and we set it equal to 0. So I subtract 12, 24x equals negative 12, divide by 24, x equals negative 1/2. Now, some of you would think that you're done at this point, but remember, it's literally called inflection point, right? There can be more than one, but inflection point means you have an x and you have a y. You have an x and a y. So we're going to use the table feature. We'll use our calculator. We're going to go to y equals, and let's put the original, not the first derivative, not the second derivative. The thing I always want to emphasize is that we're trying to find the inflection point of the original. We're trying to find the extrema of the original. It's all about the original, okay? And I know it can be a little confusing with derivatives and all that, but don't lose the point. Plus 6x squared minus 72x minus 30. Okay, then I figured out what the point is. It's negative 1/2. So I go to the table feature, second graph, delete, negative 0.5, or you can put a negative 1/2. It's up to you. And you get the result 7. Okay, so you found the inflection point, negative 1/2, 7. But we need to prove it. We need to show that's an inflection point. An inflection point is where it changes from concave up to concave down, or vice versa. So you're like, well, how am I supposed to figure out a window? And the answer is, it's what you need to see. I need to see negative 1/2, 7. That's what I need to see. So I'm going to build a window around that. So I'm going to go from maybe negative 5 to 5, maybe negative 5 to 10 or 15. You just build a window around it. And if you're like, what if I'm wrong? What if you're wrong? Change your window. You can change your window 1,000,000 times if you want. So let's just start with negative 5 to 5. So I'm going to go to window, negative 5 to 5, counting by ones. Then I'm going to go to 5 to 10. I'll still count by ones. Now, again, you're like, how am I supposed to know? You just try it. You build around what you want to see. And I'm going to hit graph. And if I'm happy with it, I'll leave it alone. Are you happy with it? Not at all. But we got a starting place, right? I do see negative 1/2, 7, but there's a lot of other stuff going on. But what do I need more of? More x, more y, more what? I definitely need more y, both ends, right? So let's change that first. So I'm going to go to window. I did negative 5 to 10. Let's do negative 20 to 20. And you're like, well, how do you know? You know by just playing around with it, right? Have a start. We know how to manipulate things. I'm just going to do it. So I'm going to do negative 20 to 20. And you said the y. So let's see what happened. Hit graph. Getting closer. So was 20 enough? Nope. So what do you want to try now? Let's do 100. Negative 100. And again, I don't need to see all this. You just kind of want to see the whole graph, which is great. I only needed to see that point, so I could have stopped, but I appreciate that you want to see the whole graph. So negative 100 to 100. I'm going to count by tens this time. Let's see how that does. Almost. Not even 100's enough. 150? Again, because you want to see the whole thing. Because you want to see the whole thing. We don't need to see the whole thing. But it is good practice of playing with a window. Let's do 50s. Negative 150 to 150, counting by 50s. There we go. That you wanted to see the whole graph. Now, again, don't forget the point. We're trying to find our point. Remember a little trick? Press second trace, second trace, second trace. Number 1 for value, number 1 for value, number 1 for value. And the value we found was negative 0.5. So you're telling, go to the calculator, find me on the graph, negative 0.5, and you find that location. Okay, so let's do just a quick sketch, we went to 150, I think, 150, and we went to negative 150. That. Something like that. And then we found that inflection point. Now, notice at this location, the inflection point, what happens? We go from a sad face to a happy face. That's what an inflection point is. It's when it goes from a happy face to a sad face, or a sad face to a happy face. That's where it changes. Now, you're probably saying, well, what's the value of that? Let's say the housing market is crashing, right? Which then people are going to start buying houses and all that stuff. And you're like, well, should I buy now? Should I buy now? Should I wait? Well, if you can find the inflection point, here's what should happen. It's still going to go down some, but then what will happen? It's going to recover. So you have this period here after this inflection point to start making some moves, right? Because you know it's going to turn. So for example, right now, I would say the market went up a lot for housing, and now it's getting a little stable, and everyone's like, it's going to crash, it's going to crash. Well, if it crashes, then you should buy something, blah, blah, blah. But if it doesn't, there's going to be a reason why it crashes, but it may stay stable in Florida, who knows? But it's all about trends, finding the right time. That's how it all works, okay? Now, we learned this thing called inflection point, and we're going to use it. And there's a bunch more examples and problems and all that stuff that you can work on. But we're going to use this in something called curve sketching. We're going to really, really analyze a graph. And remember, it's all about the original. It's all about the original. So when I say analyze a graph, the first thing we're going to do is we're going to find the x-intercepts and the y-intercepts. Now, this is an old concept. To find the x-intercept, you make y0. To find a y-intercept, you make x0. So before you walked in the door, all of you knew x-intercept is when y0, a y-intercept is when x0. So that's an old topic. We're just bringing it back to find the x and y-intercepts. That could give us some information about the graph. The second thing we're going to do, and they kind of make it really wordy, but the second thing we're going to do is find the extrema. And if I say find the extrema, that means stationary singular endpoints. Stationary singular endpoints. And then the third thing we're going to do is we're going to look for inflection points. So after we find the extrema, we're going to look for inflection points. And then at the end, we're going to give a little summary. We're going to say, hey, we found some extrema, we found some maxes, we found some min, we found some inflection points. We're going to label what we found. Okay, so basically, I've taught you everything you need to know, and we're just going to review it all. We're going to do probably a standard problem, and then I'll give you one a little bit harder. And that little bit harder means fraction, decimal, blah, 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 blah. Okay, but let's start with a straightforward problem to begin with. So I'm going to ask you to analyze the function f of x equals x cubed minus 3x squared. So that's the function. And we're going to go nice and slowly. We're going to go step by step. And we're going to catch ourselves what we know, what we don't know. Okay? So number one, I want you to find the x-intercepts. Could be more than one, could only be one, could also be none, and y-intercept. And I'll give you the hint. To find an x-intercept, you make y0. To find a y-intercept, you make x0. There's no derivatives. There's nothing like that. It's all about the original. You learned x-intercepts. Make y0. And if you're like, where's y? Y is f of x, right? Don't forget that. Okay, so find the x and y-intercepts of this one. So for this one, how do you find an x-intercept? Well, you make y0. So this would be x cubed minus 3x squared equals 0. And if you're like, I don't know what to do, I don't know my algebra, that's going to be your problem, right? Here you can factor out an x squared, which leaves you with x minus 3. So you have x squared equals 0, x minus 3 equals 0. You get x equals 0. And you get x equals 3. Again, you need to know your algebra. And we're trying to find x-intercepts. X-intercepts are actual points. So if you put 0 and 3, you're not technically not correct. It's not a point. The point would be 0, 0, and the point would be 3, 0. Now, again, we'll verify this later. We'll verify this later, but we should have two X-intercepts at 0, 0 and 3, 0. And at the summary, we'll talk about that. Okay? Then, how do you find a y-intercept? A y-intercept is where you make x 0. So this would be 0 cubed minus 3 times 0 squared, y equals 0. Again, that's not a final answer, but you would have a y-intercept at 0, 0. You would have a y-intercept at 0, 0. Now, if you got it, fantastic. If you didn't get it, algebra, 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 algebra. Okay? Now, that's step one, x and y-intercepts. X and y-intercepts, x and y-intercepts. Should be straightforward. I hate to use the word, but it should be basic. Stuff you learned in like beginning algebra. Okay? Now, that was step one in analyzing the graph. Step two is the extrema. So you're going to find the extrema for the original function, f of x equals x cubed minus 2x squared, which means you're going to be doing stationary, singular endpoints. No domain was given. No domain was given. You're going to make a table and you're going to graph this thing. Okay? So practice extrema. This one's not a hard one or anything like that. This will be a straightforward basic one. Okay. So stationary singular endpoint. Stationary, you take the derivative, 3x squared minus 4x, set it equal to 0. Again, algebra, algebra, algebra. Okay? Oh, did I write it down wrong? Hold on. Make sure I didn't write the problem down wrong.
Minus 3x.
Oh yeah, it's 3x. Sorry about that. I wrote it down. That's 3x. So if you made that change, sorry about that. So that should be 6x. I wrote it down wrong. Okay. Then we're going to factor out a 3x, which leaves you with x minus 2. Set each piece equal to 0. So we have 3x equal to 0, divide by 3, x equals 0, x minus 2 equals 0, add 2, x equals 2. Now again, these are possible extrema. We don't know yet till we actually work on it. Okay? Then, singular. Singular, we look at the derivative. Is there any dividing going on? Is there any chance that this could be undefined? Any number we could plug in at all? No. How do you know that? Undefined means dividing by 0. We're not dividing by anything. There's no x in the denominator. So none. Endpoints. They didn't give me any endpoints. So none as well. So the only two places that we need to check are 0 or 2. They both come from stationary, which will be a top of a mountain or a bottom of a valley. And when I plug them in, I plug them into what? The original. It's all about the original. So I go to y equals, I clear what I have, and we have the original, make sure I don't mess it up this time, is x cubed minus 3x squared. Okay? So the two numbers we're going to plug in are 0 and 2. So we go to our second graph for the table. We plug in 0 and we plug in 2. So those are the two possible extrema, 0, 0, and 2, -4. Okay. That comes right from the table. Now, at this point, I have no idea. Is it a max? Is it a min? What is it at all? I have no idea. And I'm not going to have an idea until I graph it. So the other part about this is you need to be able to graph, and we need a window that will work. Well, for the X's, we need to see 0 and 2. So what are we thinking? If we need to see 0 and 2, what window should we go from what to what? From what? -2 to 4, okay? That works. And again, if you want to need to see -4. So maybe go down to what? Maybe -5, -6. I'm going to keep it so I can count by twos. And then maybe go at least up to 2 just to see what's going on there, right? And again, there's not a perfect answer. It's just build around. You know you're correct if you can see 0, 0, which we can, and 2, -4, which is what we can. Those are the two places we want to see. So we go to the calculator, go to window, -2 to 4, counting by ones. Then we did -6 to 2, -6 to 2, counting by twos. Okay. Hit graph. It goes up, goes down, goes up, down, up. And it goes up again. Now that I have the graph, what do we have at 0, 0? We have a local max. What do we have at 2, -4? A local min. Okay, so far, notice that I'm highlighting on purpose. We've discovered a local max at 0, 0. We've discovered a local min at 2, -4. We also know that there's 2 x-intercepts and 1 y-intercept, and 1 point actually is all of them. 1 point is an x-intercept, it's a y-intercept, and it's a local max, all at the same time, 0, 0. Okay, then we get to 3. We get to 3. Some of you may have already started on it, but I'm going to give you some time to work on it. For number 3, squeeze it in here. Number 3, you're going to find the inflection point. Inflection point. And I'll write it down correctly this time. The original is x cubed minus 3x squared. Now, you don't have to make a new graph. We're just going to verify using the same graph, find the inflection point. Find the inflection point. Could be more than one, we'll see. And then use the graph to see if it is an inflection point, and that will help us analyze a graph. So for the inflection point, remember we're going to take the second derivative. So the first derivative is 3x squared minus 6x. The second derivative is what we use for the inflection point, which will end up being 6x minus 6. We set the second derivative equal to 0, add 6, add 6. Hopefully we didn't have any algebra issues here. 6x equals 6 divided by 6 divided by 6. X equals 1. Now again, it's not 1. A lot of times people put 1 and you're not going to get full credit for just 1. It's literally called an inflection point. So we have the 1. Do I plug the 1 into the original derivative or second derivative? Original. It's all about the original. It's all about the original. So I go back to the table. I'm going to plug in 1. When I plug in 1, you get -2. When I plug in 1, you get -2. So we have an inflection point at 1, -2. But before I say that, let's check it. +1, -2. Is that inflection point? Is that where it changes from a sad face to a happy face or vice versa? Yep. It starts sad and it ends happy because next week is spring break. All right. Okay. Now, one last thing I'm going to add is now that we have the graph, we can talk about this graph. Now be careful. I want to know, when is the graph increasing? And I want to know, when is the graph decreasing? Now, I know it's easy for you to say, oh, there it is, it's going down. There it is, it's going up. But we have to have a way that we can communicate that. So let's talk about decreasing. When is the graph going downward? And the graph is going downward, I'll do it in yellow, this portion here. Are we okay? How do we explain that? We're going to use interval notation. It goes downward from 0 to 2. From 0 to 2, from 0 to 2 is where it's decreasing. Decreasing. Now, in green, this is where the graph is increasing, increasing, increasing. Okay? Now, this is where it gets a little more tricky, because where does this thing start? What are we going to call this? Way, way down here. Negative infinity, all the way to what? To 0. And then some of that, we put a U to mean union. Where else? Or just put and. I'm good with either one. And where does it start? 2 to infinity. Now, some of you are wondering, why did I use parentheses instead of brackets? First of all, infinity always gets parentheses because it never quite ends. And these locations, 0 and 2, it's not increasing or decreasing, it's flat, right? It's a max, it's a min. So that's why you don't include them, because they're not changing at that point. They're going up before that, they're going down after that, or the other way around. Are we okay? So take a minute. When I ask you to analyze a graph, that means x-intercepts, which we found 1. X-intercept was, x-intercept was 0, 0, and 3, 0. We can verify that in the graph. Y-intercept, we have 0, 0. Extrema, we have a local max at 0, 0, local min at 2, -4. We have an inflection point at 1, -2, and we know the graph is increasing from negative infinity to 0 and from 2 to infinity, and the graph is decreasing from 0 to 2. That's what I mean by analyzing a graph. Now, I'm going to introduce a problem, but we're not going to finish it. But I'm going to introduce a problem, and I'll put it in terms of a word problem. Put them in terms of a word problem. So we're going to look at example 7. We're going to introduce it, and you'll finish it at home for next time. A discount appliance store is selling 200 large screen TVs monthly. If the store invests X thousands of dollars in advertising campaign. So remember, every word problem, we need to know what is the input, and we need to know what is the output. So the input, which is X, is ad campaign in thousands. Okay? The output estimates that the monthly sales will be given by this function. Your output, which is n of x, is monthly sales. So before we even try to solve a word problem, you have to understand the word problem. Understand the word problem. And in order to understand the word problem, we're trying to say, if I spend this $1,000 in advertising, I hopefully make some money, right? And I hopefully make more money than I spent on the advertising, or I just wasted my money. Does that make sense? So this function talks about how much money you spend on advertising in thousands and how much money I make per month. How much money I make per month. Is that part clear? And bottom line, I'm not going to get too crazy into this problem, but we're just going to analyze it. So we're going to use this problem and we're going to analyze it. So to give us a little bit more space, I'm going to kind of go here. This is a good place to have some space. And I'm going to kind of set it up for you, but I want you to try it at home. Don't forget about it. Practice it. And this will be a nice review of being halfway through chapter 4. Okay. So you're given the function 3, well, let's do it in X, not T. x cubed minus 0.25 x to the 4 plus 200. Let me make sure I wrote it down correctly. Yep. And you are given a domain. So be clear that you're only going to spend between 0 and 9, which represents $0 to $9,000 on advertising. So basically your budget for advertising is $9,000. Am I going to spend all of it? Am I going to spend 0 of it? How much am I going to spend on advertising? We already talked about the input and the output. I'm just going to structure it. You're going to work on it later. But number one, you're going to see if there's any x-intercepts and y-intercepts. I will tell you for this one, I'm going to put a star by the x-intercept. It's a little tricky to find the x-intercept. You'll get the x-intercept when you graph it. So try it. If you get stuck, don't worry. There's a little weirdness with the x-intercept, but it will become clear once you graph it. Okay? So you're going to find the x-intercept, the y-intercept. That's number one. Then number two, what's number two? Extrema. So practice your extrema. And again, you should be, as soon as you hear the word extrema, first thing that comes to mind is stationary singular endpoints. What goes along with that after you do the work is making a table and then having some sort of graph. And again, definitely take more space than I'm giving you. What's number three? Inflection points. And then number four, when is the graph increasing, decreasing? Okay. Now, this is not a crazy hard one. This is not a crazy easy one. I'd call this one a middle problem, kind of a standard problem. The decimal may give you a little bit of trouble, this and that, but that is where we're going to stop today. Please, 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 please practice this.